Lesson 7-2, solving exponential equations. In an exponential equation, the independent variable is an exponent. When we work out the property of equality for exponential equations, b has to be greater than 0, but it cannot be 1. You're going to have b to the x power equaling b to the y power if and only if x equals y. So the bases must be the same, and if the bases are the same, then the exponents must be equal to each other. Exponential equations can be solved algebraically or by graphing a system of equations based on the equation. Equations of exponential functions can be used to calculate compound interest. And we're going to look at some problems with compound interest later in this lesson. Compound interest is just what is interest paid on the principal and what is already previously earned on the interest on the principal. So compound interest, you use the formula A, which is the account balance equals P, the principal amount times 1 plus the rate divided by the number of times being compounded raised to n p power with t being in years. We'll get back to that formula a little bit later today, but first let's go through solving exponential equations algebraically. So the first thing we need to do is make sure that the bases are the same. So right now our bases are not the same. This one has a base of 4. 64 is not the same as 4, but I can rewrite 64 with a base of 4. That is 4 cubed. And then if I raise that to the 7th power, that will give me base of 4. So now the bases are the same as 4, so I can take the exponents. 5x plus 1 equals the exponents. 3 times 7 is 21. Now I can solve for x by subtracting 1, and I get 5x equaling 20. Divide by 5, x would equal 4. Next, I have a base of half, and I have a base of 16. I'm going to change this one to a base of 2, so this would be 2 raised to the, fourth power, negative fourth power. Actually, not to the negative fourth, negative first power. So that's going to give us that 2 to the negative first is half. And then all of this is going to be raised to the 4x minus 16. And over here, I can rewrite this as 2 to the fourth power. And then I have raised that to the 2x minus 5. So now my bases are the same. They both have 2 in it. So now to rewrite my exponents, I have to distribute a negative 1 here. So that's going to be a negative 4x plus 16 equals, here distribute the 4, be 8x minus 20. Now I get my x's to one side, so I'm going to subtract 8x and then subtract 16. And now I'm left with negative 12x equaling a negative 36. The x by itself, I'm going to divide by negative 12, and x would equal 3. Next, solve these. I need to have the same base. So here, the common base I can have is 3. So I can rewrite this 9 as 3 squared, raised to the 2x plus 16. This one I can write as 3 cubed, raised to the 10 minus x. So this will give us 4x plus 32 equals 30x, or 30 minus 3x. I get our x's to one side, so I'm going to add 3x. Then I'm going to subtract 32. And I get 7x equaling negative 2. And divide by 7, x would give us a negative 2/7. Next one, need to keep common bases. So common base would be 2. So this one I can write as 2 to the fourth, 64, so 2 to the 6th power is 64. So 2 to the 6th power raised up to 3x plus 6. This has to equal 2 to the 9x. So we have 9x equaling 18x plus 36. Going to subtract 18x. That gives us a negative 9x equaling 36. Divided by negative 9, x would equal a negative 4. Moving on to example 2, solve an exponential equation by graphing. Since it began in 1966, the extremely high viewership of the Super Bowl has led companies to pay millions of dollars to advertise for just 30 seconds. The average cost of a 30-second advertisement during the Super Bowl can be approximately modeled by an exponential function where the initial cost is $58,000 and the average cost increases by 9.9% each Super Bowl. Part A, we need to write an exponential function to represent the situation. Part B, we're going to estimate during which Super Bowl the average cost of a 30-second ad first surpassed $1 million. Since we want our amount in millions, the initial amount is $58,000. So if we put that as millions, we would have to move this decimal place 6 places to the left. So that would give us an initial of 0.058 times 1 plus the rate. Here the rate would be 9.9%. So the rate as a decimal is 0.099. And then raise that to the t power or x. So if I simplify it, this will give us 0.058 times 1.099 raised to the x power or t. So we put that in our calculator. Y equals, clear everything. We have 0.058 parentheses 1.099 end parentheses raised to the x power. Our Windows setting, just going to deal with positive numbers, so 0. Let's make the maximum. Let's make this 50, count by tens. Y minimum 0. To make the maximum, let's make this 500, and we'll count by 50s. Let's see if this one shows up. Since we put these down, so I need to change my Windows settings a little bit. Let's make this the maximum. Let's make this just 50. And we'll count by twos. See if that one shows up a little bit better. Shows a little bit right there. So another thing we need to do is write a system with it. So we need to see when it gets to $1 million, which will be represented by 1. So now let's go back to our calculator. And our y equals, we're going to put a 1 here. Here, the maximum, let's just make this 10. And this one, let's go 10 as well. By ones. These are count by ones. See now from here. Might have to expand my x so we can see. Yeah, let's change this back to 50, count by tens. Y maximum We can keep the y maximum there. Comes up. The other one. Oh yeah, I didn't put the. Let me delete this. Put the one in the wrong spot. So 1. Now graph it. Okay, so we want to find out when it first reach a million or surpass a million. So a second graph, we can see when it goes past the 1 mark, that would be right here. 31 is when it first surpasses it. So if we were to find that 30 points, so that was 31, it was 1.08. So if we find the intercept, so if we go to graph, find it where it intercepts, second, trace the intersection point number 5, hit enter 3 times, gives us 30.16. So that would be during Super Bowl 30. So it was during Super Bowl 31 that the average cost surpassed 1 million. So this would be about Super Bowl 30, Super Bowl 31. Next, Streptococcus pyogenes or S. pyogenes is a bacterium responsible for many human illnesses, including strep throat. The bacterium has a doubling time of about 30 minutes. Write a function that represents the number of S. pyogenes cells Y after X minutes in an experiment that begins with 150 bacteria cells. And in part B, we're going to use a graphing calculator to find how many minutes there will be in 1,000 bacteria cells. And then C, we're going to make some assumptions when we find our answer. So for an exponential function, it needs to be in y equals a times b to the x power format. So a being what we start with, and it says they're starting with 150 bacteria cells, and it's doubling. That means the base is 2 raised to the x power. So that would be our function, but it says doubling about 30 minutes. So if it's doubling every 30 minutes, x is the number in hours, so we're going to do that every 30 minutes. So that'd be twice in 1 hour. So we'll do x divided by 30. Then we're going to use a graphing calculator to find after how many minutes there will be 1,000 bacteria cells. So we graph our graphing calculator, our y equals, clear everything, and we'll type in 150 parentheses 2 raised to the x divided by 30. Let me add another parentheses in here. So raised to the parentheses x divided by 30. There we go, hit graph. I'll have to change my Windows setting again here. So the maximum, let's see, we will do, keep that 50, maximum, y maximum, let's do, there has to be at least 1,000, so let's do 5,000, and we'll count by 1,000 here. Try this one. Make this 1,000. Now graph it. I need to expand this, my Windows settings, so the maximum, let's do 200. counting by 50s, and graph. There we go. Second trace, number 5 intersect. Click 3 times for enter, and it says 82.1. So that would be about 82.1. So to the nearest tenth, 82.1 minutes. What assumption do we have to make that it continues to double exactly every 30 minutes? Otherwise, it wouldn't be exactly there. So the assumption, it doubles exactly every 30 seconds, or every 30 minutes. Next, the moment you drive a car off a dealer lot, it begins to depreciate or lose its value. In 2017, the average price of a new pickup truck was $41,000. You can use an exponential function to model the value of a pickup truck over time. Part A, if the value of a pickup truck depreciates by 9% per year, write a function that represents the value of the new 2017 pickup truck y after X years. If it depreciates, the value is 91%. So this would be, it starts off with 41,000 times 0.91 raised to the x power. Now, if we use 30, like a 41,000 here, we could use, when you put it in our calculator, we could use just 41. Otherwise, yeah, we'll use 41 here. So on our calculator, go to our y equals, this would be, we'll make this 41 times 0.91 raised to the x power. Delete the rest of this. The other one, we want to get to 20,000 or 20. So now if we change our Windows settings, so the max, let's just make this 100, count by tens. The y minimum 0, this one, let's go maximum as 50, count by tens. Now hit graph. Here's the other one. We want to find out where they meet. Second trace, number 5 intersect, hit enter 3 times. And it tells us 7.6 to the nearest cent, or to the nearest tenth of a year be 7.6 years. Next, Luciano deposits $1,700 into a savings account that pays 1.8% annual interest compounded monthly. What will be the balance after 5 years? So the compound interest formula, A equals the principal amount times 1 plus the rate as a decimal divided by the number of times compounded per year raised to the nt power. So they want to know what is the balance be after 5 years. $1,700 times 1 plus the rate as a decimal would be 0.018. Compounded monthly means 12 times a year. And this would be 12 for 5 years. So on our calculator, we'll type it in exactly the way we have it. We have 1,700 times parentheses 1 plus 0.018 divided by 12 and parentheses raised to the 60th power, because 12 times 5 is 60, equals, and then we'll do it to the nearest cent. So the account balance would be roughly $1,859.97. Next, Hakeem invests $2,500 in an account that pays 1.8% annual interest compounded daily. Write an equation that represents the A after T years. What will be the balance of Hakeem's account after 10 years? Round to the nearest cent. So A equals 2,500 times 1 plus the rate as a decimal, 0.018. Daily means 365 days, so 365 times 10 years. So we'll grab our calculator. Second trace, so we put everything in here. So it says 2,500 plus 1.08 divided by, this would be 365, end parentheses, raised to the parentheses, 365 times 10, end parentheses, equals. So that's going to give us $2,993.03. And our last question, if Aisha deposits $500 in a checking account that pays 0.9% annual interest compounded twice a month, what will her account balance be in 25 years? So we would start with the principal amount, $500 times 1 plus the rate as a decimal, 0.009 divided by twice a month. There's 12 months in a year, twice a month would be 24 times a year. Raise to the 24 times 25. So our account balance to the nearest cent, grab our calculator, 500 times parentheses 1 plus 0.009 divided by 24, end parentheses, raised to the parentheses 24 times 25, end parentheses. That will give us to the nearest cent $626.13. So that is our lesson today on solving exponential equations.